We are going to right now look at doing another tutorial. This would be tutorial 9, and this is looking at the linear optimizer within NDS. Dr. Buzz Burhans is just going to do a quick overview of some of the features, some of the workings of the linear optimizer. So I'm going to turn it over to him, so go ahead, Buzz.
Thanks, Dave. NDS has two optimizers, a nonlinear optimizer, which optimizes using the underlying CNCPS model, and it has the linear optimizer, which optimizes strictly using the analytical parameters and does not incorporate modeling. I've set up a demonstration diet, and the cows are producing about 75 pounds of milk. The inputs are set to 75 pounds of 3.8 and 3.25. It's roughly based on a real dairy. Notice that the starch level in this diet is 28.7, which is quite high. So the objective of our optimization will be to reduce the starch level. And we're also interested, if you look at the two hays that are in the diet, they are basically 25% of this first hay and 3/4 of the other hay, so 25-75 ratio. We're going to try to change that ratio to 50-50 of the two hays. So the first thing we need to do is click on the Optimizer tab. When we get over to the Optimizer tab, we can notice a few things. In this column right here, the existing diet amounts are brought in from the main recipe page, and we are automatically given some values for the minimum and maximum of the feeds that are in the diet. We can, if we want, select all of the feeds that are present here and elect to reset the constraints, or we can right click and remove all the constraints and start over again. Before we start though, it would be a good idea to go up here to the settings page. So on the Optimizer tab, there is a sub-tab called Settings. There we want to make sure that we're checked into the linear optimizer. We will optimize, in this case, on a dry matter basis. On your own, you may wish to explore these two features here, the continuous optimization and the back to recipe after optimization. Continuous optimization means that every time you change a constraint, it will immediately apply that new constraint. This is particularly useful sometimes if you're fine-tuning a mineral and, for instance, you change the calcium constraint and you have calcium available in the ingredient list, or limestone or calcarb. It will immediately affect the amount of calcarb in there. The other checkbox that we're not going to use here is the back to recipe after optimization. This checkbox, when it's checked, makes the program throw us back onto the recipe page immediately after the optimization is completed. My preference is to continue to work here on the optimization tab. I often need to refine those before I actually evaluate them back on the recipe stage, so we're going to leave that unchecked for now. Back here, we are going to look for a minute and reset our constraints. We will start by coming up here though and choosing create specification, and we'll just regenerate the specification for all the feeds in the diet. So what you see is that it has created a min and a max which bracket the existing amounts. Those amounts though may not be consistent with what we want to do or with some of the constraints that we're going to apply on individual feeds. So let's look at how we can customize those constraints. So for instance, one thing that we said we were going to do was move the proportion of these two hays to a 50-50 ratio of each other. So that means that these constraints are not going to work. So let's just, to give ourselves plenty of room, let's set the upper constraint at 20 pounds for both of those two feeds, and we'll set the lower constraint at 1 pound. So that gives them plenty of room to work. The producer has indicated he wants to continue to feed the same amount of corn silage, or perhaps as much as 1 pound more. So to accommodate that, we will manually set the corn silage to a 30-pound minimum, which is where it is now, and he said he would feed 1 pound more, but no more than that. Notice that this diet had straw in it to start with. I'm going to select the straw and the mineral, and I don't want those to move while I'm optimizing. We want the mineral fixed because it's already been created appropriately there, and the straw in this case will fix that too. So having selected the two ingredients, by holding down the shift button and then tabbing onto them with the cursor, I can choose fix min and max to the current level and agree that I want it. And now you'll notice that the min and max for straw and my mineral placeholder are fixed to the amount over here that's in the existing diet. Now I need to go down and look at these ingredients here. So I'm just going to arbitrarily say, okay, I'm willing to feed up to 6 pounds of soybean meal, up to 2 pounds in this case, just for the sake of the exercise, of canola meal. On the corn grain, we're willing to feed no more than the existing 13 pounds. And on the barley, we are willing to feed up to 5 pounds, which is what the existing amount is. Now, blood meal, we don't want to enter into this. We're not interested in that. It's in our list of ingredients over on the recipe page. So we have two options. We can right-click and delete it from the specification. Or if it's something that we're going to want to use, for instance, in another version of this diet, we can double-click on this green button, and that will remove it from being considered in the optimization, but it continues to leave it present in our ingredient list. Let's say that we want to allow it from none to 3 pounds of soy hulls, and we want to allow it from none to 5 pounds of beet pulp. On the corn distillers, we are willing to go up to 5 pounds if it will take it, and he's got some of that contracted perhaps, so we're going to set the minimum on that at 2.5 pounds. The Amino Plus, we are willing to feed up to 5 pounds of that in this case. And the Megalac, he has indicated he's willing to feed up to 1/4 pound more. Since we're going to be removing some starch, it may end up calling for some more fat to replace the energy that we're going to lose, so we'll set that constraint appropriately. Continuing with setting up our constraints, I'm going to for a moment set the ingredient constraints down here in this box to dry matter basis instead of as fed basis. And I'm going to do that because I'm going to go up to the mixing ratios, and in the mixing ratios I'm going to check the two ingredients that I am concerned about their ratio, and I'm going to type in as a percentage what percent I want of each one. Notice that it will total up to 100%. I typed in just the first one and it totals up to the second one as well. Suppose that I wanted though to change also the ratio of corn silage. So let me cancel out of this and then come back up here and reset the mixing ratio. So just for the purposes of showing you how you can do this, I would select the 3 ingredients. And let's say that I want the ingredients to be 80% hay, and of the hays they're going to be 50-50 and 20% corn silage. So I've selected the 3 of them. That to get 80% hay, and each one is 50-50, I need the first hay to be 40% of the ratio, and it defaults to kicking out the other 2 values, but they're not what I want. I want the other hay also to be 40% ratio, and I want the corn silage to be a 20% ratio. So 40, 40, and 20 adds up to my correct proportions that I'm interested in, and I can then hit confirmation, and the optimization will respect those. Now, just for the purposes of this exercise, I'm going to remove the corn silage because we're not interested in using that in this demonstration, and we will set the two ratios to 50-50 on the two hays. Having done that, we'll again check the confirmation. Turning our attention to the right side of the screen, we have the nutrient parameters and constraints that we can apply. In this case, they are populated with the default values for the nutrient specifications for the linear optimization. Those default values are created previously in the Utilities tab on the Parameters button. Then you select the specifications and set up what you want there. On the yellow column, we have the values that are in the existing diet. That's back on the recipe page. And then these default values are here. In this case, since this diet is a 17.5, we're not going to touch too much. We would like to, in this case though, constrain that not to be more than 17.75% protein. It's interesting here that the NRC energy value for this diet is 0.7662. I'm going to put that in there as a 0.7662 again so that it is matched. However, that doesn't mean that the optimization will give me a diet that produces about 75 pounds. We go back over to the recipe page. Remember that up here this pen was producing about 75 pounds and the diet supports about 75. When we use the linear optimizer here, the optimizer does not run its optimization through the model. So on the lower part of this screen, we can see the model nonlinear parameters. And that's helpful because as this diet changes, the yellow values will also change. But the constraints, the nonlinear constraints, will not be invoked in the running of the linear optimization. So to give us approximately the same amount of milk, one thing that you might do is add the NEL from the NRC in there and see how close that comes. To actually get the same amount of milk as we had before will require us to either, once we have a diet that's fairly close, go ahead and use the nonlinear optimization then, or to manually tune it till we get what we want. So we can see these nonlinears once again when we're running the linear optimizer, but we cannot use the constraints that are available there. The other thing we said we want to do in this diet is we want to reduce the starch from 28 to no more than 26, so we'll put the upper limit of the 26% there. The ether extract, even if we pull in that extra quarter pound of Megalac, we're unlikely to hit our upper limit on that. So we should be okay to go at this point. We've set up our constraints, and then all we really need to do is hit the optimize button, and lo and behold, we find out that our model is infeasible, not an uncommon occurrence. We can explore why the model is not feasible, why it can't optimize, by looking at what's happened here to some of the indicators on the constraints. We notice that the indicator for ADF and forage NDF have both turned red, and this little marker here is on the lower side of this column. If that marker was pointing to the right, it would mean that they are hitting on the upper bound. Pointing to the left, it means they're hitting on the lower bound. So we see that the values in the current diet are lower than what the constraints are here. So strictly for the purposes of demonstration, we will reduce these lower bound constraints to the values that are actually achieved in the existing diet. We'll set those down there. These probably are not values that you might want to use. This value down here on the MP supply is also red, but I am unable to change that, and it doesn't matter, as we've said, because these nonlinear constraints will not be respected. So once we've made these changes, we'll hit the Optimize button again, and we are still infeasible. Looking around at the ingredient constraints, I observed that the original diet had a 48.9 pound dry matter intake, and my constraints are both less than that. So for the purposes of the demonstration, I'm going to set that upper limit to 49. I don't like to set the upper limit much higher than the existing in most cases because it's somewhat deceptive. If my diet produces more milk, for instance, it may just simply be that I've given it more dry matter intake to work with. So we're going to set this between 48 and 49, and we'll try once again and see if our optimizer works. We're still infeasible, so we need to do some. So what we can observe on the ingredients is the constraints on the ingredients are so tight that it will not be possible to lower them enough to reduce that starch. So what we're going to want to do is, let's suppose that we want that we'll allow the barley to go down by 3 pounds, and we will allow the corn to go down by 2.5 to 10, and we'll see if that gives us the space that we need to accomplish our optimization. We'll hit the Optimize button, and sure enough, that got us out of trouble, and we now have a new diet. We can evaluate the success of our optimization first by looking at our nutrient levels and seeing if they remain fairly consistent with what we desire. We notice that the NEL value has turned red, so when a red value appears in this column, it means that that constraint has not been met. But it's quite close, as we see, and it did meet the starch value, which we see right there. It did drop the starch level down, so given that the starch level dropped, we still have a reasonable NEL value. We look like we're going to be okay. The value for the ME supply looks fairly similar to what it was before, and then remembering that that's simply a way to look at whether this diet is going to be close on the allowable milk. If this ME supply had dropped, for instance, to 90, we would know that this diet will not support the same amount of milk, even though it's met our constraints. However, remember that it's a linear optimization we're doing, and it will not respect or invoke these nonlinear constraints. When we look over here to the ingredients, the revised diet now shows up in this yellow column. So no longer are we looking at the original recipe diet here, we are looking at this revised diet. We see that the corn silage stayed within the constraint that we wanted it to. It has changed the amount of hay, but now we see that these hays look like they're approximately 50-50. On a dry matter basis, we can check that. That's how we set that on a dry matter basis. And we observe that on a dry matter basis, in fact, they are exactly 50-50, which was what we asked for. Going back to the as-fed amounts, we can review what we've got here for constraints or for amounts. And again, these little pointers are telling you whether that ingredient is hitting on the upper or lower bound. So anything that's pointing to the left is hitting on the lower bound. We fixed these two, so we're not surprised that they are hitting there or they're staying there. It would have reduced the soybean further than what we allowed it to. The soy is hitting on the lower bound, and it has pulled in some beet pulp here. The barley flakes are also hitting on the lower bound. Our megalac has stayed the same, and the distillers, if you remember what we had that at before, I believe is going to higher than what we had originally. So the diet looks reasonably okay. We then can go back to our recipe page and do further evaluation of the diet. We see that we did come somewhere close to where we started in terms of the allowable milk. Again, we can see that the starch over here has dropped from 28 to 26, and we would proceed with evaluating our results and either hand tune them or go back and refine our constraints, or go back and use the Nonlinear Optimizer and run this through the model. It's often easier to start with the Linear Optimizer and get a diet that looks pretty much what you think it should look like. Either do that or put one in there by hand manually, and then run the Nonlinear Optimizer. The Nonlinear Optimizer is a powerful tool, but it needs the starting diets to be somewhat close to where you think they're going to end up. It has a harder time making big changes in ingredient amounts. The Linear Optimizer can move the ingredients all over the place fairly easily. And the last thing I might point out is, if you wanted to compare these diets, we can go up to the Comparisons tab, and we should have two comparisons showing up here. So here is our original diet on the left, diet number 1. We can see the ingredient amounts there, and recall that we had a ratio on those two hays of 25-75, and our new ratio is 50-50 on a dry matter basis. And we can look down, and the corn distillers ethanol was 3 1/3 pounds, and it's now up to 5 pounds. So we pretty much can see what has happened. If we want to evaluate the model effect, even though we didn't run this through the model, we can do that down here. We can look, for instance, at our carbohydrate comparison, and here we would see, for instance, that if we look at the amount of starch that is degraded in this second diet, we see that we had 21.7% of the dry matter was degraded starch in our first diet, and as we reduce that starch, that degraded starch has gone down, so this diet should probably be a little bit healthier. The percentage of starch that was degraded hasn't changed, and that makes sense because our starch sources are basically the same, and we didn't change them radically in terms of proportions or anything like that. Had we used more barley in this run and less corn, we would have seen that the starch degraded as a percent of the starch changed more than it did here. But basically the proportions are pretty much the same. The other thing that becomes interesting to look at is the total carbohydrates that are degraded, and we see that our diet has produced as a percent of dry matter a decrease in the total amount of carbohydrate that we've degraded. That's still a fairly high amount of carbohydrate there that we have degraded. So hopefully that gives you an idea of how the Linear Optimizer works and how to set the constraints, how to manage the ingredient constraints by fixing them or opening them up, how to use the mixing ratios, and then how to come back and evaluate your diet and evaluate the changes you've made by using the Comparisons tab.